All right, so we're going deep on collapse theories. They offer like a really unique perspective on how the quantum world and like our everyday experiences, they might actually work together.
Yeah, and it's cool how collapse theories, they like acknowledge that quantum stuff is super strange, but they don't just stop there. They actually try to connect those kind of fuzzy quantum possibilities to the world that we see, the definite world.
Exactly. It's like quantum mechanics gives us this awesome set of tools for understanding the microscopic world. But then when we try to use them on the big stuff, the macroscopic, it just doesn't seem to work?
Yeah. It's like take Schrodinger's cat, right? That famous thought experiment. In regular quantum mechanics, the cat's both dead and alive at the same time until someone actually checks. But that doesn't really make sense, does it? Like in our everyday lives. So collapse theories try to solve that. They say the wave function, the thing that describes the cat's state, collapses on its own. It picks a definite outcome, like heads or tails.
So no more zombie cats running around.
Not if these theories are right. They add in something that makes sure big things, like cats or, I don't know, chairs, they settle into one state super quickly. No more of that weird, both at once stuff that quantum mechanics allows.
Okay, I can see why philosophers are into this. But before we get too deep into collapse theories, can we take a step back? Like, remind ourselves about the important parts of standard quantum mechanics.
Totally. So the wave function, it's like the heart of quantum mechanics, right? It describes, mathematically, all the possibilities for a quantum system. It doesn't say exactly where a particle is or what it's doing, but it gives us the chances of finding it in different spots or states.
So it's like a map of possibilities, not a set plan.
Exactly. And this wave function, it changes over time. It evolves according to the Schrodinger equation. That equation basically tells us how the probabilities, those chances, change as time goes on. This evolution is linear and deterministic, meaning it follows a smooth, predictable path.
Okay, I'm following so far. So where does it all get weird?
Well, one of the craziest parts of quantum mechanics is this thing called the superposition principle. Basically, it says a quantum system can be in multiple states at the same time until someone measures it. Imagine, like, a coin spinning in the air. It's both heads and tails until it lands.
Right, that's where the whole Schrodinger's cat problem comes up.
Yeah.
But why does measuring something force it to pick just one state?
That is a great question. And that, my friend, is the measurement problem. Standard quantum mechanics just doesn't explain how measuring something makes the wave function collapse. It's like the theory is missing a piece.
So that's where collapse theories come in, right? They try to fill in that missing piece of the puzzle.
Exactly. They add some tweaks to the standard quantum mechanics setup, specifically to the Schrodinger equation, to make it account for this spontaneous collapse.
So they're like adding a new rule to the game.
Yeah, you could put it that way. They put in some nonlinear and stochastic terms into the Schrodinger equation. These new terms introduce some randomness into how the wave function evolves, kind of like adding some rough waves to a calm sea.
And these rough waves, this randomness, is what makes the wave function collapse, even if nobody's measuring anything.
Precisely. And here's the cool part. The more complex the system, the more often these collapses happen. A single particle might go a long time without collapsing, but a huge object with tons of particles, it's constantly collapsing.
Ah, so that's how they get rid of macroscopic superpositions.
Hmm.
A cat's always being hit with these collapses so it can never be in two states at once.
Exactly. That's how collapse theories make the strained quantum world fit with our everyday experience of a clear, classical world.
Okay, this is starting to click, but can we get into some specific types of collapse theories?
Definitely. The GRW model, that stands for Ghirardi-Rimini-Weber. It's one of the first and most famous.
GRW? Okay. What's the basic idea?
In the GRW model, every particle has a tiny chance of suddenly localizing. It's like a sudden hit that shrinks its wave function, making its position more certain.
So it's like the particle's possibilities get squeezed into a smaller space.
Yeah, exactly. Think of it like a big cloud suddenly shrinking down to a little raindrop. Now, for one particle, these hits are super rare. But when you have a bunch of particles together, the chances go way up.
Right, there's that trigger again. Big stuff gets hit all the time, small stuff, not so much.
Exactly. So for a big object, these hits happen so fast that it basically instantly settles into a definite state. No more weird quantum superpositions for things we can see.
GRW, got it. Are there other collapse theories out there?
There's CSL, that's continuous spontaneous localization. Instead of sudden hits, CSL says the wave function is constantly evolving in this random way, kind of like it's always being nudged toward collapsing.
So it's a gentle push instead of a sudden jolt.
Exactly, like a cosmic breeze that's always guiding the wave function. Both GRW and CSL, even though they work a little differently, they're both trying to do the same thing. Make sure big things act classically while still keeping the success of quantum mechanics for the small stuff.
This is all super interesting from a physics perspective. But for someone who's into philosophy, why should they care about these collapsing wave functions?
That's where primitive ontology comes in. It's basically asking, what is this theory actually talking about? What's the real stuff that the theory is trying to describe?
Okay, I'm listening. Tell me more about these primitive ontologies.
When you're talking about collapse theories, there are two main ones: the flash ontology and the mass density ontology.
Okay, let's take them one at a time. What's the flash ontology about?
With the flash ontology, those hits, those localizations, they're the real deal. Each one is an actual physical event in space-time. And the world we see, it's made up of all these tiny localized events all happening super fast.
So it's like reality is flickering, coming in and out of existence, kind of like a strobe light.
That's a really cool way to put it. It's a totally different picture than the smooth, continuous reality we usually think about.
And the mass density ontology, how is that different?
The mass density ontology says that the fundamental stuff is this field of mass density that's spread out in space, and it's always changing. It's more continuous. The wave function is just a way to describe this mass density. And those spontaneous collapses, they make sure that the mass density becomes clear and localized, especially for big objects.
So it's less about things suddenly happening and more about this cloud of stuff that's constantly shifting and being shaped by the collapses.
Right. And this idea, it helps explain those tails of the wave function we talked about before.
The tails, you mean those little bits of the wave function that stretch out forever even after a collapse?
Yep, those. They've bothered some physicists who think about the wave function in the traditional way. But when you're thinking about mass density, those tails aren't a problem. The mass density out in those tails is so tiny, it doesn't really matter.
So those tails are just a mathematical quirk, not a real physical issue.
Exactly. This is why these ontologies are so cool for philosophers. They make us ask, what's really real? What's the world made of at the most basic level?
This is blowing my mind. But I'm wondering, how do we even know if any of this is right? Are there experiments that could show us if collapse theories are true or not?
Now we're talking. That's where it gets even more interesting. Unlike some quantum mechanics interpretations, collapse theories make predictions that we could actually test. They don't always line up with standard quantum mechanics.
So we could actually settle this debate in a lab.
Totally.
Tell me about these tests, these experiments.
One really promising area is doing diffraction experiments with these really big molecules, macromolecules.
Macromolecules, like the ones that make up DNA and proteins. Those huge molecules.
Those are the ones. We can actually make interference patterns with them now, but regular quantum mechanics says that shouldn't be possible if the molecules have a definite position. But collapse theories, they say those random localizations should blur the patterns a little bit.
So it's like we're looking to see if those big molecules are actually getting those hits.
Exactly. Another cool area is using optomechanical interferometers.
Octo what now?
Optomechanical interferometers. They use light to measure tiny movements of a mirror. The idea is to make the mirror be in two places at once, a superposition, and then look for any signs of noise that would only happen because of those collapses.
Okay, so instead of molecules, we're looking for collapsing mirrors.
Haha, yeah, kinda. And there are experiments trying to find X-rays that are given off spontaneously from germanium. Standard quantum mechanics says a stable atom shouldn't do that. But collapse theories say those random collapses can jostle the electrons in the atom, and that makes them give off X-rays.
So it's like those collapses are leaving behind clues, and we're trying to find them.
That's a great way to think about it. And there are tons of other ideas floating around. We could use cold atoms, those are atoms that are super controlled, to see if there are any collapse effects. Some people even think we could use the noise in those gravitational wave detectors, like LIGO, to test collapse theories.
Wow, we're talking about using the most advanced tech we have to see if these theories are right. This is amazing. But hold on, I have a question. We've been talking about how collapse theories connect the quantum and classical worlds, but what about Einstein's theory of relativity? Do they get along?
That's a big question, and that takes us to a really exciting frontier in collapse theories, figuring out a way to describe them in a way that fits with relativity.
Relativistic, like making sure they work with Einstein's ideas about space and time.
You got it. It's a tough challenge. Regular quantum mechanics already has some issues with special relativity, particularly with the idea of locality, the idea that things can only be affected by what's right near them.
Right, because Einstein showed us that nothing can travel faster than light.
Exactly. But quantum mechanics has this thing called entanglement, which seems to allow spooky action at a distance.
Entanglement. Isn't that when two particles are linked, even if they're super far apart?
That's the one. It's like they're talking to each other instantly, no matter the distance. So the question is, do collapse theories make this spookiness even worse? Not necessarily. Actually, John Stuart Bell, the physicist who came up with those famous Bell's inequalities, he thought that collapse theories might actually fit better with relativity than standard quantum mechanics.
Really? That's unexpected. Why would that be?
The kind of non-locality you see in collapse theories is different from the one that's a problem for standard quantum mechanics. In regular quantum mechanics, there's parameter independence, which means what you measure on one entangled particle can instantly affect the other one, no matter how far apart they are.
Yeah, that sounds like sending a message faster than light, which Einstein says shouldn't happen.
Exactly. But collapse theories, they show outcome independence. This means the results you get when you measure entangled particles can be linked in a way that breaks Bell's inequalities, but you can't use that to send information faster than light.
So the results are connected, but you can't actually send a message faster than light.
That's the key difference. And that makes it much easier to make these theories work with relativity.
Okay, that makes sense. So maybe collapse theories aren't so incompatible with relativity after all.
That's what it's looking like. And physicists are actually making some progress in making relativistic versions of these theories. One way is to use a multi-time wave function, where every particle gets its own separate time variable.
So like each particle has its own little time zone instead of a single universal clock.
Yeah, you could think of it that way. Another way is to add a new field that controls the collapse process. But this new field has to play nice with both special and general relativity.
So like a cosmic glue that makes everything stick together according to Einstein's rules.
Haha, yeah, that's a good analogy. It's a really exciting area of research. If we can figure out a collapse theory that's truly relativistic, it would totally change how we understand the universe, from the smallest particles to the biggest structures.
This has been an incredible crash course on collapse theories. I'm already looking at the world a little differently.
It's a super fascinating area that brings together physics and philosophy.
But before we wrap up this part of our deep dive, I have one last question. We've talked about how these theories try to solve the measurement problem. But what about consciousness? Where does that fit in?
That's a question that's caused a lot of debate. Some early ideas for solving the measurement problem tried to bring consciousness in as something that triggers the collapse. But the collapse theories we have now, they don't need a conscious observer for the collapse to happen.
So it's not like those ideas that say our thoughts create reality.
Nope, not at all. These theories are based in physics. The collapse happens no matter if there's a conscious observer around or not.
Okay, but even if consciousness doesn't cause the collapse, do these theories have anything to say about consciousness itself?
That is a great question, and one that we'll be tackling in the next part of our deep dive.
Okay, I can't wait. Join us next time as we continue to explore collapse theories and dive even deeper into their philosophical implications.
Looking forward to it. Welcome back to our deep dive on collapse theories.
Yeah, it's crazy how these theories make us question like the most basic things about the world. Last time we were talking about how collapse theories fit with Einstein's theory of relativity, but I want to go back to those primitive ontologies. They seem super important for understanding the philosophy behind collapse theories.
You're right, they're key. Remember, primitive ontology is about figuring out what a theory thinks are the most fundamental parts of reality. What's the real stuff the theory is describing? With collapse theories, we have two main options: the flash ontology and the mass density ontology.
Okay, let's break those down a bit more. If I remember correctly, the flash ontology is all about those sudden localizations, those hits that make the wave function smaller, like reality is being constantly redrawn moment to moment.
Exactly. Think of it this way. Reality is kind of like a mosaic, and those flashes of localization are like the individual tiles. Each hit is a real physical event happening in space-time, and the world we experience is built from all these tiny localized events.
So it's a universe of quick moments, always appearing and disappearing. That's a pretty different picture from our usual idea of a stable, continuous world.
It definitely is. That's what's so cool about collapse theories. They challenge our deepest intuitions about what reality is.
Now, the mass density ontology gives a slightly different perspective. It's less about those sudden flashes and more about a field that's constantly changing.
Yeah, you got it. The mass density ontology says that the basic stuff of reality is the mass density, and it's spread throughout space. It's a more continuous idea where the wave function is just describing this mass density, and those spontaneous collapses, they just make sure this mass density is well defined, especially for big objects.
So it's not so much about sudden events. It's more like a cosmic painting that's always changing.
That's a fantastic analogy. This perspective gives us some cool ways to think about those tails of the wave function we talked about earlier.
Right, those tiny bits of the wave function that go on forever, even after a collapse. It's a tough one to wrap your head around.
Well, with the mass density ontology, those tails aren't really a problem. Sure, they stretch out infinitely in a mathematical sense, but the actual mass density they represent is so tiny, it doesn't really matter.
So those tails are more of a mathematical quirk than a philosophical crisis. That's good to know.
Precisely. The mass density ontology gives us a neat way to deal with that issue, but it also brings up some really interesting philosophical questions, like if mass density is what makes an object, and this mass density is never really zero, even far away from the object, what does it even mean for an object to have a boundary?
That's a great point. It's like the object's influence, even though it's tiny, stretches out forever.
Yeah.
Makes you wonder where an object ends and empty space begins.
Exactly. It challenges how we usually think about boundaries and makes us think differently about what it means for something to be in a specific location.
It seems like both of these ontologies, the flash and the mass density, they both make us rethink some really basic philosophical ideas like what reality is, what measurement means, and even what makes an object an object.
Absolutely. That's why they're so fascinating for philosophers. They offer a whole new way to see the world and deal with some of the biggest questions about existence.
One question I keep coming back to is about causality. If the world is really run by these random collapses, does that mean everything is just chance? Does it mess up the idea of cause and effect?
That's a huge question, and it's one that philosophers have been debating a lot. Some say that the randomness and collapse theories does challenge our usual understanding of causality. After all, if things can happen without a reason, what does it even mean for one thing to cause another?
Right, it seems pretty chaotic if we can't trace events back to specific causes.
It definitely changes our perspective, but it's not total chaos. While collapse theories bring in randomness at the most fundamental level, that randomness still follows the rules of quantum mechanics. So even if we can't predict individual events, we can still predict the overall behavior of systems.
So like flipping a coin. Each flip is random, but flip it enough times and you can be pretty sure you'll get about half heads and half tails.
Exactly. The randomness in collapse theories works similarly. There's basic uncertainty, but the theory's predictions are still solid. This leads some philosophers to say that collapse theories don't necessarily destroy causality, they just make us rethink it.
So instead of a strict cause and effect view, maybe we need to think about probabilities and statistics.
Precisely. It's a shift from seeing cause and effect as a rigid chain of events to seeing it as a web of possibilities, each with its own chance of happening.
That's a really interesting way to think about it. It also makes me wonder if those random collapses might actually be guided by some deeper level of causality that we haven't figured out yet. Maybe it's not truly random, but driven by some hidden principle we don't know about.
That's a great insight. It's like suggesting there might be something secretly influencing those coin flips. The point is, collapse theories make us think harder about what cause and effect really means, and they open up a whole new set of questions about how events in the world are connected.
I'm also curious about consciousness and how it fits into all of this. We talked about how the whole measurement problem, the question of how quantum systems go from uncertain to definite states, is a big motivation for collapse theories. And I remember you saying that some early attempts to solve the measurement problem tried to bring in consciousness as like a trigger for the collapse. But you also said that the current collapse theories don't actually need a conscious observer for the collapse to happen.
That's right. It's a common misunderstanding to think that collapse theories rely on consciousness. But the truth is, the collapse mechanism is built into the theory itself. It's a physical process that happens whether or not there's a conscious observer around.
So it's not like those new age ideas that say our minds are creating reality.
Not at all. Collapse theories are rooted in physics. The collapse is objective and doesn't depend on any subjective or mental stuff. However, the connection between collapse theories and consciousness is still super interesting to explore.
Okay, I see what you mean. So even if consciousness doesn't cause the collapse, maybe the collapse process is important for understanding how consciousness comes about.
Exactly. That's the subtle but important point. Some philosophers and physicists think that collapse theories might give us a way to understand how consciousness emerges from the physical world.
So the idea isn't that consciousness makes things collapse, but that the collapse process itself might help create consciousness.
Precisely. It's a pretty speculative idea, but it's based on the idea that consciousness might be something that pops up in complex systems, especially ones that are good at processing information, like the human brain. Some people argue that the collapse process, with its randomness and its ability to choose definite outcomes, could play a role in that emergence.
It's wild to think that consciousness might come from the dance of collapsing wave functions happening in our brains.
It is. And while it's just a hypothesis right now, it shows how collapse theories can make us think in new ways about some of the biggest mysteries of existence.
Okay, let's change gears a bit and talk about the experiments being done to test collapse theories. We've talked about some of the experiments being proposed, but what's the current situation? Is there any solid evidence for or against them?
That's the big question. Unfortunately, the answer isn't simple. We discussed earlier how collapse theories make very specific predictions that are different from standard quantum mechanics. But these differences are usually super tiny and hard to spot.
So it's like searching for a needle in a haystack.
Even trickier, it's like trying to hear a whisper in a hurricane. The effects we're looking for are often hidden by noise and limitations in our equipment.
So we're basically waiting for technology to catch up so we can really test these theories.
It's not just about better technology, it's also about being clever and coming up with smarter experiments. We need experiments that can make those tiny collapse effects bigger and easier to see.
So it's going to take a combination of ingenuity and better technology to solve this puzzle.
Exactly. The good news is that the field is moving forward. Those experiments we talked about with macromolecules, optomechanical systems, and X-rays, they're all pushing the limits of what we can do experimentally. And there's a growing feeling that we might be close to a breakthrough.
It sounds like an exciting time to be working in this field. There's a lot at stake, and the potential payoff is huge.
Yeah.
If we find strong evidence for collapse theories, it would completely change how we understand quantum mechanics and the nature of reality itself.
No doubt about it. It would be a massive shift in our scientific worldview. But even while we wait for that clear experimental proof, there's still so much to explore with the philosophical side of these theories.
This has been an awesome journey so far. We've explored the core ideas of collapse theories, talked about those fascinating ontologies, looked at how they relate to relativity and consciousness, and discussed the experiments being done to test them.
We've definitely covered a lot.
But I feel like there's so much more to discover. Join us for the last part of our deep dive, where we'll explore the bigger picture of collapse theories, think about how they might change our view of the world, and maybe even venture into a bit of science fiction to imagine what a future with collapsing wave functions might look like.
I'm excited to explore those uncharted territories with you.
All right, welcome back to our deep dive into collapse theories. We've been on quite a journey, haven't we?
We have. From those crazy ontologies to those experiments that are pushing the boundaries of what we can measure, it's been a wild ride.
And in this last part, I'd love to really dig into the bigger implications of these theories. We've talked about how they change our view of quantum mechanics, but what about our worldview in general? How could they change the way we understand ourselves and our place in the universe?
Now that's a fantastic question, and I think it gets at the heart of why these theories are so fascinating, not just to physicists, but to anyone who's ever wondered about the big questions of existence. One of the most striking things about collapse theories is how they introduce this basic randomness into reality itself.
Right, it's like the universe isn't this perfectly predictable machine anymore. It's something a bit more unpredictable and spontaneous.
Exactly. And that has huge consequences for how we think about those big philosophical puzzles like free will, the direction of time, and even the limits of what science can explain.
Okay, let's unpack those one by one. First up, free will. This debate has been going on forever, and it seems like collapse theories are adding a whole new layer of complexity.
They definitely are. The traditional debate about free will is all about determinism versus indeterminism. Determinism says that everything, even our choices, is set by things that happened before. Indeterminism, on the other hand, leaves room for chance and randomness, the idea that the future isn't fixed.
And it sounds like collapse theories, with those random collapses happening all the time, are definitely on the side of indeterminism.
You could say that. Those spontaneous collapses bring in randomness that we can't predict or control. And some philosophers see this as a possible way out of the determinism trap, a way for free will to exist.
So if our choices are influenced by these random quantum events, then maybe it's not all predetermined. It's like those collapses are injecting some real freedom into the mix.
That's the general idea, though of course it depends on how you define free will in the first place. It's still hotly debated, but it's a fascinating possibility that these theories have brought to the table.
It really is. Okay, what about the arrow of time? You mentioned earlier that collapse theories might shed some light on why time seems to move in only one direction, from the past to the future.
Right, the arrow of time is one of those big mysteries in physics. Our current understanding of the laws of physics says they should work the same whether time is moving forward or backward. But obviously, that's not how we experience time. We remember the past, not the future. We get older, not younger.
Yeah, there's a big difference between the physics and how we actually live time. How do collapse theories try to explain that?
Well, some people think that the collapse process itself might be what creates the arrow of time. The idea is that each collapse is a one-way event, a point where all those quantum possibilities are narrowed down to one actual outcome. It's kind of like a ratchet, making sure time can only move forward.
So those random collapses are like the ticking of a cosmic clock,
Hmm.
pushing time in one direction.
This is a big deal. It suggests that the arrow of time might not be a fundamental feature of the universe, but something that emerges from the collapse process.
That's such a cool concept. It really changes how we think about time itself.
It does. And it leads us to our last big question. What does this mean for scientific explanation? One of the most important things in science is the idea of causality, finding those cause and effect connections. But as we've been talking about, collapse theories introduce randomness that shapes up our traditional ideas about causality.
Right, if those collapses are truly random, it's tough to trace events back to specific causes. Like you can't really explain a dice roll with logic.
That's it. And this has some philosophers of science wondering if collapse theories can really give us satisfying explanations. If things can happen without a clear cause, how can we truly understand why they happen?
That sounds like a pretty serious challenge to the whole foundation of science.
It is, but it also gives us a chance to rethink what makes a good scientific explanation in the first place.
So are you saying we might need to move away from that deterministic view where everything has a neat and tidy cause and effect explanation?
I think we need to be open to the idea that the universe might be a bit messier than that. Collapse theories, by bringing in randomness, are pushing us toward a view of science that relies more on probability and statistics.
So instead of looking for a single cause for something, we might need to think about multiple factors and probabilities. It's a shift from looking for absolute certainty to being okay with uncertainty.
Exactly. And we're already seeing this happen in areas like climate science, epidemiology, and evolutionary biology. These are fields where we deal with complex systems using patterns and probabilities, not just simple cause and effect chains.
It seems like collapse theories are encouraging us to have a more sophisticated view of science, one that's comfortable with complexity and accepts that our ability to predict things has limits.
I think that's a great way to put it. And this goes beyond just science. It affects how we see the world as a whole. Collapse theories encourage us to view the universe not as a rigid, predictable machine, but as a dynamic, ever-changing system where chance and randomness are fundamental parts of the game.
It's a humbling thought, isn't it? To realize that we might not have all the answers, that there might be inherent limits to what we can know about the universe.
It is humbling, but it's also liberating. It frees us from the idea that we can know everything for sure and opens up a whole world of possibilities. It lets us embrace the mystery and wonder of the universe, to see the beauty in its complexity, and to keep exploring with curiosity and awe.
I love that. I think that's a perfect place to wrap up our deep dive into collapse theories. What a journey it's been.
It really has. We've explored the weird and wonderful world of quantum mechanics, tackled some seriously deep philosophical questions, and got a glimpse of how our scientific and philosophical understanding of the world could radically change.
And to everyone listening, we leave you with this. If the universe really is governed by these spontaneous collapses, what does that mean for the nature of reality, the flow of time, and what it means to exist? Keep thinking about these questions, keep exploring, and keep asking why. After all, that's what makes us human. The desire to understand the universe and our place in it.
Until next time, keep searching, keep questioning, and keep diving deep.